let us start building arithmetic circuits for just normal fixed point numbers that are whole numbers, no fractions, okay? And we want to start with the old buddy, the adder, all right? So we go back to, I don't know when you guys learned this. Is it preschool where you look at adding numbers together? Well, the cool thing about our class is it's even easier than preschool because we only have two symbols. So we start off by saying, all right, well, let's do this. What are all possible sums for adding 0 and 1 together? Okay, so you do, okay, well, I'm going to go 0 plus 0 is equal to, go ahead and give me the answer. 0, thank you. Then you go 0 plus 1, and what's that answer? 1. And then you go 1 plus 0, and that's equal to what? 1. And then you go 1 plus 1, and you go, ah, crap. I'm out. What is it? It's 0. Except you had to bring on another bit position, so you had to actually say, well, it was actually 0 was the sum, and 1 was what we call a carry. And the reason we cared about that is because when you build a circuit, you're going to build an adder with a combinational logic circuit, okay? How many bits is the output of a combinational logic circuit, like a sum of products? It's 1, right? So when you write this expression and you have like an AND gate going into an OR gate, it's only going to be 1 bit, okay? So that means when we have to really take into account this whole notion of we're only going to produce the sum using 1 circuit, okay? If we want to have a carry, that's another circuit, okay? So we actually have to do 2 circuits just to add 2 bits together, all right? Luckily, it isn't that big of a deal because we're pretty savvy. We can actually put this into a truth table and actually figure out what the logic is. So let's say that I have a circuit which is A and B, and these are just bits that are coming in, and I'm going to add them together, and I'm going to create an output called the sum. And let's go ahead and make one that's going to be called the carry, but let's call it the carry out. Okay, so we'll call it the carry out of the circuit. And we'll see why we had to put out there in a second. So I go, okay, A and B, going to go to my truth table here, and the truth table, all possible input values for A and B are going to be 0, 0, 0, 1, 1, 0, 1, 1. Okay? And we list out the output that we need for the sum, and that was 0, 1, 1, 0. So I go 0, 1, 1, 0. And then I want to do the output for C out, which I only had it right here. So what's going to happen with over here? Is there a value here for this carry? Yeah, it was actually 0, right? So we didn't have a carry, but if we were going to build a circuit to produce a carry, we would just have it be 0 for those situations. So our carry is actually 0, 0, 0, 1. 0, 0, 0, 1. So let's build 2 circuits to implement these outputs. Should we get a K-map? Should we bring on model sim? What do you want to do here? Phone a friend? Can you recognize what this circuit would be for sum? What was it? Yes! Exclusive OR. So I could actually say, all right, well, I'm going to build a circuit, and let's go ahead and draw this bigger so we can put our gate in there. We're going to have A and B come into this. And to create the sum, we'll go ahead and put an exclusive OR gate. All right, that's cool. This dude comes here. This guy comes over here and goes boom. All right, we did it by inspection. Now, can you produce a circuit for C out? Does anybody recognize that pattern? An AND gate, you say? Well, you are correct. So let's go ahead and put an AND gate right here. And that will be C out. And we'll go ahead and pop A and B in there and say, boom, this is an adder. Ha! What do you think of that? It's not just an adder. It's not even a full adder. It's a half adder. Okay? The name of this circuit is half adder. Okay? Half adder. And you go, well, that's interesting. Why is it a half adder? Well, it's because what are you going to do with this carry bit? First of all, you're never going to have a circuit that just adds 2 bits together. That's stupid, okay? What you're going to do is you're going to have a byte of information added to a byte of other information. Or you're going to have a 32-bit word added to a 32-bit word. So immediately, like within, we've only been doing this for less than a minute, and we're already to the point where it's like, we need to actually get bigger numbers in here. So if I think about what I need to do, I need to have the following. Let's just say I wanted to add a nibble together. So I'm going to have a nibble, okay? And I go plus something like that, okay? Just add these up. And I start off and I say, okay, can I do it? 1 plus 1 is what? 0, and the terminology we use is 0 with a carry. And look at this. Now I got 1 plus 0 plus 1. I have to actually add that carry in to the next higher order sum. Isn't that cool? Now let's just complete it just to warm up that part of the brain, the part of the brain that does binary math. Okay? So 1 plus 0 plus 1 is what? It's 0 with a carry. 1 plus 0 plus 1 is what? 1 didn't have a carry, but we could have actually said, well, the carry was 0, but yeah, well, whatever. Then we had 1 plus 0 is what? 1. It's like, oh, that's kind of interesting. Okay? Horrible example, but it did warm up that part of the brain. Okay? Let's do this one. 1, 1, 1, 1 plus 1, 1, 1, 1. Okay? All right. So let's go. 1 plus 1 is 0 with a carry. Holy moly. 1 plus 1 plus 1. Does anybody remember what that is? It's 1 with a carry, isn't it? Holy crap. 1 with a carry, 1 with a carry, 1 with a carry. So this is crazy because two things emerged from this little exercise. The first thing is that if we're going to build a circuit to perform multiple bit addition, how many inputs does it need to have? It needs to have 3. It needs to account for A and B, which in this situation would be the bits in that position, okay, of the inputs, and a carry in that comes from the lower position sum. Okay, so we got 3 inputs. The other thing that's interesting is that if I built a 4-bit adder, we would potentially not only have a 4-bit sum that comes out of it, but we would have a carry out. And the carry out of it would be how many bits? Only 1. Okay? So if I came along and I said, all right, well, I'm going to draw this adder now, and it's going to be a 4-bitter. So I could say, well, let's call this A and this B, and I brought this, and then the sum would be 4 bits, but then I'm going to have a carry out of the entire thing, which is going to be 1 bit, or we don't even write that on there. So, interesting, a couple things needed to happen there. So, what should we do? How the hell are we going to do this? How do you build a combinational logic circuit? Well, let's just do it the way we did it old school a couple months ago. Let's do a truth table. All right, we got our brain warmed up. So let's take a look at how we're going to do this. If this is going to be a circuit, okay, it is going to have A and B coming into it, okay, but it's also going to have a carry, what we're going to call in. So this little guy right there is going to be C in, and that's from the lower position sum. So what we can have is we can actually put this in truth table form and say, I'm going to have C in, A, and B. And what we're trying to build is we're trying to build the 3-input adder that I will use for every position within this arithmetic operation. So we're actually going to use 4 of these circuits. All right, well, let's go for it. If there's 3 inputs, how many possible input codes are there? 2 to the n, always, is correct, which is we evaluate to be carry the 1, 8. Okay, so I got 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, boom. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. All right, life is good. And it's going to have a sum, okay, and it's going to have a C out. All right, let's go. Here we go. 0 plus 0 plus 0 is what? Let's do the sum first. This is pretty easy. 0 plus 0 plus 0 is 0. 0 plus 0 plus 1 is 1. 0 plus 1 plus 0 is 1. 0 plus 1 plus 1 is... What the hell is it? 1 plus 1, it's 0 with a carry. Let's just go ahead and put the carry over here. Great use of a dotted line, right? Good Lord. They look like ones. Problem solved. Okay? And then I come down here and I go 1 plus 0 is what? 1. 1 plus 0 plus 1 is 0 with a carry. And then 1 plus 1 plus 0 is 0 with a carry. 1 plus 1 plus 1 is, that's our weird one, it's 1 with a carry. Okay. All right, life is good. We actually filled them all in, so let's go ahead and fill in C out. We already listed all of our carries out, so let's fill in the zeros. And it goes 0, 0, 0, 1. Is that right? And then 0, 1, 1, 1. Okay, feels good. How the hell are we going to do this? Well, we got a 3-input puppy. Why don't we put it into a K-map and see what happens? Okay, so let's do the sum first, since it's a weird one. I can't quite recognize what the pattern would be. So I'm going to go into a K-map, and I slappy, 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 and I come along, and I'm going to put up here these two variables. So I'm going to go C in and A, and I'll put B there, and that allows me to do this. 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, and I can slap these puppies in. 0, so I go 0, 1, 1, 0, and then I jump over here and I go 1, 0, 0, 1. All that's left now is just circle groups of 1, which we can have how many? Blah, this sucks. You can't circle anything. I drew that K-map for no reason. Except, does anybody notice a pattern emerging here? Does anybody remember this from 261? We covered it for almost 4 seconds one time. Does anybody remember what a checkerboard pattern results in gate-wise? It's an XOR gate, right? And it turns out that this right here is nothing more than A, so the sum comes out to be this. Sum is equal to A exclusive ORed with B exclusive ORed with C in. So it's this whole checkerboard thingamajig. Okay? And remember, there is no such thing, or the way that XOR gates are built is it's always a cascade of two input XOR gates. So when you do this, this is the same logic as saying I have an exclusive OR gate feeding into an exclusive OR gate. Okay, so that's how you get the logic. So if you went along and you exclusive ORed these guys together, it'd be pretty cool, because let's just say we did exclusive OR of A and B. Okay, so I'm going to go 0, I'm not even going to look at C. I would get 0, 1, 1, 0, right? All right, that's cool. And then if I did it again, I'd get 0, 1, 1, 0. So now I have 0, 1, 1, 0, and I would have to take that dude and exclusive OR it with 1, and what would I end up getting? Well, I'd get 1 exclusive OR with 0 is a 1. 1 exclusive ORed with a 1 is a 0. 1 exclusive ORed with a 1 is a 0. 1 exclusive ORed with a 0 is a 1. So I proved to myself that this actually works, and I did it through a method called what? Proof by exhaustion, which is a fancy way of saying I just plugged in all the inputs and got the output. Okay? So I proved to myself that this circuit will indeed work. Okay? So if I just need 2 exclusive OR gates and I can produce the sum of 3 bits. Piece of cake. All right. How about C out? This one is not necessarily a checkerboard pattern. It is something that we could put in a K-map. So let's go over to here and do a K-map. So I'm going to come over here and I'm going to say, all right, slappy, slappy. Slappy, slappy makes daddy happy. Has anybody seen Trolls? Perhaps probably don't have kids. C in A and B. 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. And let's go. 0, 0, 0, 1, hoppy, 0, 1, 1, 1. All right, well, I can group some of this stuff. So I got myself a group, and I got myself a group. All right, so let's go ahead and write the expression. So I'm going to say C out is equal to, and it's like, okay, here we go. I'm going to have myself an A ANDed with C in. Okay, that's going to be this prime implicant right here. And then I'm going to have ORed with, and let's do this one right here. It's going to be A ANDed with B, okay? And then I'm going to go ORed with, and I'll do this one right here, it's going to be B ANDed with C in. Okay, so that's my circuit. Cool. Now, here's where the kind of the cool part of this comes along. You can do some algebraic manipulations in order to get to a circuit which is a lot easier. And it's going to take a few steps. So let's do this. I am going to do the following. I have two circuits. Okay, I have this circuit right here, and I have this circuit right here. But I would like to try to reuse logic operations. This is the whole idea in digital systems of design reuse. So it's just this principle of if you could break something down into like something that you design once, design a circuit, lay it out, build it, and then use it over and over and over, that's very effective, okay, in terms of engineering and also understanding how the thing works. Sometimes you might say, I'm going to take a circuit or a logic expression, and I'm going to manipulate it and rearrange the terms in order to use something that already exists. And when you do that, it might actually be slower, but you went for the design reuse over everything else. Okay? So what we are going to try to do, we are going to manipulate this puppy right there to try to get it into a form that I can exploit using some of my product terms that I already have. Okay? Namely, XOR gates. Okay? And I didn't mean to say product terms, I meant to say logic terms. Okay? So here's what I'm going to do. All right? I have at my disposal exclusive OR gates, and I want to try to reuse those. Okay? So let us rearrange this guy. We'll bring it on down. I'm going to have myself a C out, and I'm going to go equal, and I'm going to say A ANDed with C in, ORed with A ANDed with B, ORed with B ANDed with C in. The first thing that I'm going to do is I'm going to use the distributive property and rearrange this in order to take the C in terms and pull them out. So I'm going to rewrite this like this. I'm going to rewrite it as A ANDed with B, ORed with A, ORed with B, ANDed with C in. Okay? So all I did was I said I recognized that C in was a term that was ANDed with both A and B, so I pulled it out. Okay, so I pulled it out to get to here, and that left A ORed with B. So that's a distributive property. Okay? Now, why the hell did I do that? Well, it turns out that if I look at this, okay, I'm looking right here, and I go back to that original circuit that I built. Does anybody remember this little fella right here? The half adder? That was a nice little circuit. Okay, it's pretty easy. Just was a 2-input XOR gate and a 2-input AND gate. And I say, I want to reuse that guy. So if I have an exclusive OR gate, okay, and I have an AND gate, okay, and they sit within this block, one of the things that I could do is say, this is kind of cool. Look in here, if I brought A and B into this thing, I would have A ANDed with B. Okay? And if I use these things right here, I don't have A ORed with B. Okay? I would rather have that be something else. But I do have another AND gate that I could use. Okay? So let's think about trying to do design reuse with this half adder to get our sum, and then let's see what is existing there that I could potentially use. So what I'm going to do is I'm going to build a circuit that looks like this. I'm going to have a half adder. I'm going to call it HA1. Okay? And then I'm going to do a half adder again. I'm going to call that HA, we'll call that 2. Okay? And within here, you're going to have an exclusive OR gate. Boom. And you're going to have an AND gate. Boom. Same thing here. We already designed this. It's already sitting there. It's a little component for us. And we're slapping. Okay? And I'm going to have an input that comes here, an input that comes there, an input that goes like this, boop, and an input that goes like this, boop. Okay? And then down here, same thing. I'm going to have an input that goes here, boop, input that goes there, boop, and then this input's going to go there, boop, and this guy goes up here and goes boop, and boop. All right, so life is good. I feel so good. And what I would like to do is the following. Let's create the sum, which is A, exclusive OR with B, exclusive OR with C in, which is going to sit right here. So I've got sum. In order to do that, let's just bring A right here, boom, B right here, and guess what I get right here? I have A exclusive ORed with B. And then I need another exclusive OR gate, so I come over to here, and then the only thing I need to do is bring C in over here. And guess what I got for my sum? I now have A exclusive ORed with B, exclusive ORed with C. This is pretty sweet, okay? What else do I have at my disposal since I wired them up like that? Well, this right here is what? This is A ANDed with B. Okay, that's kind of handy. And then this right here is actually something else too. This is, it's like I've got A exclusive ORed with B, and then it's ANDed with what? It's like ANDed with C in. So this is ANDed with C in. So this is what I have. Okay, this is what I have at my disposal. Okay? All right, life is good. Life is good. Check this out, though. Look at this little fella. That dude looks just like that dude, so I got that for free. Okay? And then, look at this guy right here. Doesn't this guy look like that guy? It looks like it. Looks can be deceiving. If I could just flip that little fella into an exclusive OR gate, you know what I'd have? I'd have this term and this term taken care of, and all I'd need to do is OR those together. So I'd only have to add another OR gate in order to produce the sum, which would sit over there. Now you're like, what the hell are you going to do? Well, I'm going to hypothesize that this circuit, this logic expression, is equal to another circuit, which is A ANDed with B, ORed with A exclusive ORed with B, ANDed with C in. I propose that these two are equal. Okay? How can I prove it? But I'm going to go all the way back to proof by exhaustion. Okay? Because that's just like so easy and so fast. So I walk up to it and I do the following. Okay? First of all, let me redraw all of my truth tables really quick so you can read them. Bam! Okay? Now you're like, holy, is this in the book? I'm going to tell you a secret. Everything I'm teaching is directly out of the book. Okay? Directly out of it. Okay? So I come along and I say, I want to prove that that expression is equal to that expression. And I'm doing this just to rearrange it so that I can reuse this thing that I built, which was a half adder. Okay? So in order to do this, I'm going to do the following. First of all, let's break this puppy up into A ANDed with B. So that's kind of easy. I just go A ANDed with B. And then I go, okay, I come over to here, and then I'm going to do A ORed with B, ANDed with C in, and that's the second term. And then I go ahead and put it all together, and guess what I get? I get exactly what the answer we wanted was. No kidding. I mean, duh, that's the one that we just made, right? So of course that's the answer. The reason that I decomposed it like that was because when I put the tables equivalent to each other, I wanted to map it out for this guy right here. So now this is really the one that we think is cool. So let's break it down again. A ANDed with B is going to be identical to it. So it's going to be 0, 0, 0, 1, 0, 0, 0, 1. Okay? And then what we want to do is we want to evaluate A exclusive OR with B ANDed with C in. Right? ANDed with C in is really easy because whenever you AND it with a 0, it's always a 0. So what that means is that up here, where C in is a 0, those puppies just get zeroed out. Just zeroed. Okay? When you AND it with a 1, what's the result? Anything ANDed with a 1 is itself. So that is actually pretty easy because all you do is A exclusive OR with B, which in this situation is 0, 1, 1, 0. So those are the two things. Now, this is the new term that we're messing with. All we got to do now is OR them together, and look at what frickin' happens. These guys are ORed together. It's going to be 0, 0, 0, 1, and then here I get a 0, 1, 1, 1. Holy frick balls. Look at this. They're identical to each other via proof by exhaustion. Ha! Now, I don't know who ever figured this out. Okay? I'm going to go with John, though. It's probably DeMorgan. Okay? I should just write that. If I just wrote something in a book, do you think eventually people would believe it? You never know. They'd be like, oh, I cited Lemire's 2006. I'm like, okay. You know, how many times do you fight with a citation, right? You ever think about that? Well, don't think about it now either, because we're almost done with this. So I come to you and I say, this is awesome, because now all I need to do in my original circuit to create the half or the full adder is do this. I'm just going to bring this little puppy down. I'm going to go right here, and I'm going to put an OR gate, like an OR gate, and I'm going to OR that with this dude right here. That then becomes my C out. Okay? So I had A, B, and C as the inputs, and I had sum and C out as the outputs. And what do you think we call this circuit? A full adder. We did it. And here's what it looks like drawn professionally. Okay? So, beautiful. Check this out. What's so neat about this is that if you build a half adder, okay, like as a component in VHDL, which is very easy to do, it's just 2 logic gates, then you pop that dude, and all you need to do is take these 2 components, instantiate them, put an OR gate there, and you have built a full adder. Huh? Now, what's the next thing that you immediately want to do? You're like, man, we took forever to do that. Why don't we put them all together and make what we call a multiple bit adder? And all you do to do this is you, first of all, you redraw the circuit. Okay, so what I'm going to do is this is going to go back, and this is going to be our 4-bit adder. There's going to be 4 bits of A, 4 bits of B, and a carry in, and you're going to put it like this. You almost always draw a full adder. You almost draw all arithmetic the way that it looks positionally. Okay, so that's what, usually in schematics we go left. What we do is we go, well, it's kind of, we're messing with numbers. Let's put it just like we would write the numbers. So this is bit position 0, this is bit position 1, this is bit position 2, this is 3. And then we will have the carries go this way, and then the carry out will pop out like this. It just makes it easier to understand. When you go to implement it, who cares how you lay it out? I mean, rotate it to make it fit. But let's think about the way this works. We draw, now we're sitting here, we're like, we got inputs on the right, outputs on the left. We have other inputs, we're going to put them on the top. Is that going to freak anybody out? Okay, no? All right, good. So what we're going to do is we'll give it the subscript A0 and B0, okay? A1 and B1, and the subscript is the bit position within the nibble, or the number. And then we got A2 and B2, A3 and B3. We're actually going to bring the sum out on the bottom. So this will be sum 0, sum 1, sum 2, sum 3. And then what we'll do is we'll take the carry out from this position right here, position 0, and feed it directly into the carry in of bit position 1. And we'll take this carry out, feed it over here. We'll take this carry out, feed it over here. We take this carry out, and this is now my carry out of my whole system. The other thing you got to think about is what are you going to do with that first C in? Let me cover it slowly so you can see the answer. What do you think we should do with that? Leave it floating? Set it to 0? Yeah, because what if you add 0 to something? What does it do? Nothing. Screw it. So all we need to do is just short that to ground, and we're good to go. Okay, now this has a unique name. This is actually called a ripple carry adder. Okay, we love the word ripple. Remember the ripple counter? Now we got a ripple carry adder.